Welcome everyone to the Spoken Nerd. I'm your host Connor McDonald, and this is the podcast where we talk about database technology, really just for the fun of it. Hopefully we learn some things, but ideally it's just a great way of sharing cool information about the Oracle database and application development and database administration and anything relating to Oracle that takes your fancy. In the last episode, we spoke about segments and extents and things like that, which prompted some feedback from listeners saying, do I need to know all this internal stuff when becoming, say, a application developer or database administrator? I think the answer to that would be yes and no. Probably the best way of describing that would be to relate it to the metaphor of a car. I don't know all the internals of my car that's parked in my driveway at the moment, but it is useful for me to know the rough mechanics of how it works in terms of cylinders and pistons and the like. And also, I should be abreast of the fundamentals I might need to know in terms of looking after it on a day-to-day basis, checking the tires, checking the brakes, the various fluids that go in the engine that you're meant to be managing, say, on a weekly or monthly basis. That doesn't mean I'm going to race out and build my own car, and it doesn't mean I'll ever be a fully fledged car mechanic. And I think understanding database internals is similar. There are some people out there that probably could build a database from scratch. They have dug that deep into the internals. I think that's a fairly niche position to be in. In reality, I think just knowing the background and the concepts behind some of the internal features of the database is going to make you more competent when it comes to using their technology as one would expect it to be used, namely building applications and storing your data. With that said, given that we spoke about data files and segments and extents, I figured in this podcast we'd talk about tablespaces. You might be thinking there's not a great deal to discuss when it comes to tablespaces. After all, in a previous episode I said a tablespace is just a logical grouping of data files. And this is true, but the devil is in the detail. So let's dig into tablespaces. A tablespace, being a logical collection of data files, is where you store your stuff. Or your data from tables and indexes, anything that consumes space, will ultimately go inside a tablespace and one or more of the data files comprising that tablespace. What that means is that whenever space is required in the database, as your table gets bigger, as you create an index, etc., the database needs a mechanism of tracking where to put that data. Where is there free space in your tablespace and the data files that sit underneath it? Where is the used space? And historically, that created some issues when it came to very, very aggressively growing databases. If I have tens, hundreds, or thousands of connections all rapidly inserting data, then I might have dozens of tables growing incredibly rapidly, and therefore rapidly asking for new extents in the database. And therefore the database must be able to serve those requests to find new space very, very efficiently. We had some dramas way back in earlier versions. One of the rules of a relational database is that everything is self-describing. The database itself is described with a database, as in you can query a catalog to find out information about the database itself. The management of free space within a tablespace obeys that rule. Way back in earlier versions of Oracle, back around the Oracle 7 timeframe, we had two dictionary tables that managed where the space was being used across all tablespaces. Internally, those two tables were called UET$ and FET$. UET stood for the used extent table. FET, as you'd imagine, stands for the free extent table. An empty table space would have an entry in the FET$ table saying that all the space is available. As I allocated an extent, for example for a table or an index, I would add a row into the UET$ table saying I now have a used extent and make an adjustment to the FET$ entry to indicate the reduction of space. As we start having multiple objects, tables, indexes, etc., we start getting lots of rows in the UET$ table and multiple rows in the FET$ table as well. When I drop a table, a row gets put back into the FET$ table, indicating that that space is now free. These tables then became a contention point for high volume systems. If a lot of sessions all request space at the same time or nearly the same time, we have to make sure that we don't give the same entry from the FET$ table to more than one session. That would naturally lead to a data corruption. So there were some serialization mechanisms in place to make sure that only one person could grab a particular piece of free space at a time, and that might actually slow the database performance down if you were rapidly allocating extents. Compounding that was over time as multiple entries got put back into the FET$ table. For example, a table gets shrunk, or it gets dropped, or we drop an index, etc. It might end up being the case that I have multiple entries in that table, no single one of which is sufficiently large enough to serve an incoming request. I might have 10 1 megabyte chunks of free space, and someone came in saying, I need 5 megabytes, and we don't have a single 5 megabyte chunk to give them. To overcome that problem, the SMON background process used to come along from time to time and look for contiguous chunks. If I found 5 contiguous chunks of free space, contiguous being they lined up to contiguous points inside a data file, then SMON would take those 5 rows and consolidate them back down to a single row representing the entire free space. In that way, when large requests came in, we could immediately serve them as opposed to doing this consolidation process on the fly and therefore impacting the online performance of foreground sessions. And don't forget that around this time frame, parallel server was no longer just for a select few customers. It was becoming more and more popular. And as we know, once you have more than one server competing for common dictionary structures, that can increase the cost of that contention because multiple nodes now have to coordinate their activities with a central lock management system that spans nodes. So by the time Oracle 8i came along, there was obviously a need to address this issue as servers were getting faster and applications and databases were getting more and more busy. And the invention that solved this was called locally managed tablespaces. It's fair to say that this has been a real success story for tablespaces because no one in their right mind would use anything but a locally managed tablespace in any modern version of Oracle. As the name suggests, a locally managed tablespace doesn't rely on a central dictionary table to manage where the used and free space is. That management is done in the tablespace itself, actually in the data files that sit under that tablespace. We call tablespaces that use the historical management system of free space a dictionary managed tablespace because it was using the data dictionary to manage where the free and used space was. When you create a locally managed tablespace, typically at the front of the data file, but it doesn't have to be, we allocate some space to store a bitmap. And that bitmap simply is a sequence of bits that represents a chunk of free space or used space in the tablespace. In its simplest form, let's say the tablespace is 4 megabytes in size, we could allocate 4 bits. If the bit is set, the first megabyte is used. If the bit is unset, then the first megabyte is free, and so forth. What this means is that a tablespace, if it's going to be represented in terms of a sequence of bits, each bit must represent a consistent chunk of space. As a result, locally managed tablespaces can be thought of as being logically carved up into uniformly sized chunks of free space. As a DBA, you had control over what those chunk sizes were. When you created a tablespace, you could say, I want my tablespace to be 2 gigabytes in size, but every time I allocate an extent, that extent will be 8 megabytes in size. With that information, the database can then allocate a bitmap where each bit represents an 8 megabyte chunk, and that bit would be set or unset depending on its related extent being used by a table or index. If you've listened to previous episodes, you'll notice that this actually aligns very, very nicely to the white paper that Weinler Wazer wrote, saying that within a tablespace, all extent sizes should be the same, guaranteeing you're not going to have any fragmentation issues. Now, when you request space within a tablespace, you don't have to compete for a database dictionary object. You simply look along the bitmap at the start of each data file and find where there is an unset bit, and that's going to point to a free extent that you can now allocate and use. There is still some serialization involved, but that is now at the data file level as opposed to the entire database level. You might be thinking to yourself, doesn't this break the rule that you mentioned before about a database being describable via the database itself? And yes, we had to make some adjustments. If you query the definition for example, DBA free space, deep down inside the definition, rather than just accessing dictionary-based tables, you'll see that it references what we call $$ tables, and in this case, they really just point to the bitmaps that are sitting out on the data files. So we still give you a SQL interface into the free space information, but in reality, it also is going out and scanning these bitmaps at the front of the data files to work out where the free space is. Oracle didn't just abandon existing customers and tell them, well, if you haven't been using locally managed table spaces until now, then that's just tough luck. We created some routines to let you convert from a dictionary managed table space to a locally managed table space. And in that case, we would actually put the bitmap somewhere else in the data file where there was currently some free space. Similarly, you might be thinking, what about those create table commands that used to do things like initial extent 15 megabytes? Were they going to fail when someone converted to a locally managed table space which insisted upon, say, a uniform size of 2 megabyte extents? No, all we did was come up with some simple multipliers. So if you requested a 15 megabyte extent in a 2 megabyte locally managed table space extent size, we would give you the next size up, so 8 by 2 megabyte extents, and therefore you can serve that 15 megabyte request. Under the covers, if you go look at that bitmap, you would see that we actually allocated 8 bits worth of extents, being 8 by 2 megabyte chunks in the data file. Dictionary managed table spaces are pretty much extinct nowadays. It's impossible to create a dictionary managed table space anymore. It's simply no longer functionally available. You can see the evolution to locally managed table spaces through the versions of Oracle. We started off with just dictionary managed table spaces in 7. In 8i, we had locally managed table spaces, but they were optional. Now, I think in 9i or 10g, the default was locally managed table spaces for all table spaces except the system table space, which we'll cover in a second. And now, in all modern versions, whenever you create a database, all the table spaces, including all the internal ones like system and sysorgs, are locally managed, and that is the only option. Before we talk about the kinds of table space like system and sysorgs, etc., which I've just mentioned, there is one other recent change to the way we can structure a table space, and you'll hear the terms small file and big file table spaces. Before we can cover them in real detail, we'll need to talk about a thing called the ROWID, which will be in the next podcast episode. But it's enough to say at the moment that the small file and big file concept is simply a reflection of the fact that in times gone by, operating systems had fairly small limits on the maximum size that a single file can be on an operating system file system. Back when I first started working with the Oracle database, a typical limitation was 2 gigabytes. No file could be larger than 2 gigabytes. A data file within a table space has an internal limit on the total number of blocks that it can actually address. This was never an issue because operating system file limits were far lower than this anyway. But as operating systems became capable of handling huge files, then that internal limit on the number of blocks became a bit of an issue. That limit was 4 million blocks. So for an 8K block size, that meant a data file in an Oracle database couldn't be more than 32 gigabytes. As operating systems now allow files larger than that on some file system types, then we've made some changes to table spaces to accommodate those larger files. Such table spaces are called big file table spaces. We'll return to how a table space can contain a file larger than 32 gigabytes once we've covered off the ROWID in the next podcast episode. Let's now talk about the kind of table spaces you'll find in an Oracle database. When I first started using Oracle, there was pretty much one kind of table space. All table spaces were the same bar one, and that one was called system. That is where your data dictionary was stored. All other table spaces could be used for different things, but ultimately you were just relying on naming conventions. For example, you would have a table space typically called RBS. That was where your rollback segments would go into. You would typically have a table space called temp. That is where your sorting operations would occur. However, the underlying structure of all of those table spaces was the same. They were dictionary managed, and there was nothing to stop you from putting any kind of object in any of those table spaces. Probably the first significant improvement to that very simple architecture came around the Oracle 7.3 timeframe, where even though, yes, all the table spaces were still the same structure, we realized that when it came to sorting and temporary work areas, it's a bit of a wasted activity to allocate some space for someone to do some sorting, and then when they're finished sorting, to deallocate that space. That's just going to put more pressure on that UET$ and FET$ tables in the dictionary in terms of constantly grabbing some space, releasing that space, grabbing space again, etc. So around the version 7.3 timeframe, as we allocated temporary storage areas inside our temporary table space for sorting, etc., we would not deallocate that space when the operation was finished. We would simply mark it as being free for someone else to use. In that way, we didn't have to constantly put information back into the FET$ table indicating the space was free. It was constantly allocated. We simply redirected which session was being able to use that space. In that way, we've relieved a point of contention. That got improved upon even more around the 8i timeframe, when there was the realization that, well, we could do a lot more with temporary information if we put temporary data into its own special table space, which we now call a temporary table space. We can do things like not bothering with writing redo information when someone allocates a segment in there. If it's just temporary information, we would never need it for database recovery anyway. We don't have to back it up because it's temporary information. By having a dedicated table space, especially assigned as being of type temporary, we no longer had to back it up. We would simply create a new temporary table space if we ever had to restore the database from backup. Staying with temporary table spaces just for a touch longer, in the very latest versions of the Oracle database, when it comes to clustered databases across multiple nodes, we can even nominate what we now call a local temporary table space. In that way, we don't need to have a lot of cross-node communication just to talk about temporary information that is most typically only being required by a local instance or server anyway. Most people still use global temporary table spaces, which is the default. If you're on a recent version of Oracle and you're running real application clusters, you should check out local temporary table spaces as well, because they no longer need to be on shared storage. There's been a similar evolution of functionality when it comes to undo segments, or rollback segments as we used to call them. Around the Oracle 7 timeframe, you typically had a table space in which you would put your rollback segments, but there was nothing special about that table space. And you also always had to have at least one rollback segment in the system table space in order for the database to start. In Oracle 9, we introduced the concept of automatic undo, because it was always a bit of a black art for DBAs to correctly manage undo or rollback segments in a database in terms of choosing how many they were meant to have, how big they should be, how many of the extents they should be, when they rolled around to their fresh starting point, etc. It was a fairly complicated task. Automatic undo was an enhancement to remove that overhead from the DBA toolkit. The database would simply look after undo management for you. To do so, we introduced a new dedicated type of tablespace called an undo tablespace. And in that way, we could guarantee that the only information in that tablespace would be undo segments that pertain to automatic undo. It was just a way of guaranteeing that the automatic undo mechanisms would have unfettered access to the rollback segments in that tablespace. Even automatic undo has evolved over more recent versions. Once you get to the multi-tenant options, which came in 12c, then shortly after that in 12.2, we introduced the concept of local undo, which is an undo tablespace per pluggable database. Various facilities related to cloning of pluggable databases are made a lot easier by having local undo tablespaces as opposed to a single undo tablespace that's shared amongst all pluggables in a single container. If you're using the multi-tenant option, I'd strongly advise you check out local undo tablespaces, in this case local being relative to the pluggable database. Around the 10G timeframe, I think, we introduced the concept of the sysaugs tablespace. This is really a reflection of the way that databases have evolved over the years. Originally, when you installed the Oracle 7 or 6 database, you would have a system table space and not much else. But over time, the database started to include the Oracle text option, the spatial option, the multimedia option, and various other facilities that have added more and more functionality to the database. Each of these things typically came with their own set of schemas and their own set of table spaces. So around the Oracle 8 and 9 timeframe, it would not be uncommon to see many tablespaces in your database even before you had created a single table for your own applications. If you didn't do this and jammed it all into the system tablespace, then you had other problems where the system tablespace was getting very large and more difficult to manage. In Oracle 10G, a huge amount of management automations came along for the database. And so it was really time then to take a fresh look at how we would manage content that is being collected on your behalf inside the database. That led to the sysorcs tablespace, a tablespace that is dedicated for Oracle objects in particular. So things like your AWR repository and the other supplied schemas such as Oracle Text, Spatial, etc. will all put their objects in the sysorcs tablespace, keeping it separate from the system tablespace, which is the data dictionary, but also not cluttering up your database with dozens of other tablespaces whose names you've never heard of. Even for seasoned DBAs, the concept of system tablespace, sysorg, temporary, undo tablespaces is probably all the tablespaces in perhaps 90% or more of the databases they manage. But there are a few more niche tablespaces that it's worth covering before we finish off today. We recently introduced the concept of a shadow tablespace. In the same way that perhaps if you're at work and you have a new starter, they'll be told to shadow you from day to day to work out what you do and therefore be able to replicate that job. The same with the tablespace. A shadow tablespace replicates the data in a primary tablespace in order to provide what we call lost write protection. By having multiple copies of that tablespace, we can compare and contrast the data between them such that if we lose the write due to an operating system issue, then the shadow tablespace can be used to recover that data. Another kind of tablespace that you don't see that often is what we call the dedicated in-memory fast start tablespace. It is just indeed a normal tablespace, but it has a particular function. In-memory is a technology inside the Oracle database where large amounts of data are stored in a special in-memory structure in order to make querying very efficient and quick on those structures. However, memory is memory. If you bounce your database, then all that great valuable data that's sitting in that in-memory store would be thrown away and need to be repopulated on the next time you start your database. One of the things that the in-memory tablespace allowed you to do was when you needed to do a managed shutdown of your database, we could dump out those in-memory structures into a special tablespace and reload them straight back from there after the database is restarted, therefore avoiding the cost of repopulating from scratch that in-memory store. There's so much more we could talk about on tablespaces when it comes to the operations we could do on them in terms of read-write, read-only, transporting them, encrypting them, the concept of Oracle managed files, and we haven't even touched on one of the more critical things in terms of how segments are structured inside a tablespace called automatic segment space management. Perhaps we'll cover all that on another podcast episode, but for the time being, I think that'll do it for your understanding of tablespaces today. As always, I love to hear your feedback on these episodes, so please hit me up on Twitter if you want to talk more about tablespaces. If not, we'll see you on an upcoming podcast episode soon. Bye for now. Thanks for listening to this podcast. The music credit goes to Zanman from Pixabay Music.